study of transport process 2, and we will assume certain things that you are already aware of. For example, you know about Navier-Stokes equation, what is going to be energy equation, their uses and all. But what we have not covered in transport process 1 is the basic interrelation between heat, mass and momentum transfer. Suppose for example, you have some data on heat transfer. It is very difficult to conduct an experiment on mass transfer for that specific system. So, what one can do is using some sort of analogy can obtain the relevant equations of mass transfer from a knowledge of heat transfer correlations. Same thing is true if you have some hydrodynamic idea about the system, how can you convert that to mass transfer studies or to heat transfer. So, we are going to stress on the interrelation between heat, mass and momentum transfer from a theoretical standpoint in this specific course. The text materials are Birds, Stewart and Lightfoot as before. For heat and mass transfer, we are going to use Incropera and DeWitt, and Fox and McDonald for momentum transfer. The course loading would be exactly same as before, 20 for your class assignments or teacher's assessment would be 20, your mid semester would be 30 and end semester 50, and the grading is going to be relative. We will incorporate the lab separately. So, as far as the theoretical thing is concerned, it is going to be evaluated out of 100 and we will add the corresponding marks from the lab component as well. Grading would be relative as before. Now, the first thing that we are going to start today is study of boundary layers. Now, you have a little bit of introduction about boundary layer. If there is a hot cup, you are bringing your finger close to it. Unless and until you are very close to the hot cup, you won't be able to sense that your finger is approaching towards a hot surface. And in a region very close to the hot cup, the temperature suddenly jumps from the ambient to that of the cup. So, for each transfer processes, there exists a thin region in which most of these transfers take place. For example, if you have a solid object, a plate which is inside a liquid, and suppose the liquid is flowing over it. Due to viscosity, the velocity of the liquid adjacent to the solid surface would be that of the solid plate itself, which is the no slip condition all of us know about. If we move away from the solid plate, the velocity would decrease, and if you move maybe let us say about few millimeters away from the surface, the velocity would be that of the free stream velocity. So, at that point or beyond a very thin region, the fluid will not know that a solid plate exists. The layer, the thickness of this layer is commonly termed as boundary layer. Now, we should talk about a bit about the history of the genesis, origin of boundary layers. People know about, people used to treat the fluid flow as inviscid flow as early as in 1755 or so, when the theoretical hydrodynamics evolved from Euler's approach. So, everything is inviscid, there is no question of viscosity, so there would be no frictional drop, and you can very well imagine what would the effect be. You will never be able to match your experimental results with your theoretical prediction, because your fluid does not have any viscosity, it does not give any resistance to motion. In 1825, between 1825 and 1850, Navier and Stokes independently developed the famous equation, Navier-Stokes equation, which takes into account the viscosity of the fluid. There would be some sort of shear stress which resists the motion of the fluid. Now, those equations, though they are available, they are very difficult to use in practical situations. The problem being it is a very complex equation, and without any other theoretical knowledge or without the help of numerical computation, it is extremely difficult to solve Navier-Stokes equation for a complete flow field. So, there are two parallel ways of treating hydrodynamics, and in the 1700s and 1800s, the hydrodynamics with which people were mostly concerned about were the design of shapes. How can you design a shape which is going to have, which is going to require less amount of power to move it inside in the sea? Prandtl was the first one who conceptualized the existence of boundary layer. That means there would be a very thin region near the shape, near the surface of the shape, where the viscosity or viscous forces are going to be important. But in rest of the flow field, you can treat it as inviscid. So there can be certain approximations which are going to be valid in that thin layer, which is termed as boundary layer, and beyond which an Eulerian approach of inviscid fluid flow is perfectly acceptable. So we are going to start with that, like starting with the complete Navier-Stokes equation. If we assume that everything takes place in a layer very close to the solid surface, what are the approximations that we can incorporate that would simplify Navier-Stokes equation in such a way that an analytic solution is possible in some cases? If not, then we have to still use numerical solution even today. There are certain other approaches in fluid mechanics which we have discussed before. For example, one approach is the differential approach, and the second approach is the integral approach. In differential approach, which you have done, like the shell momentum balance or so, the governing equation that you are going to get is a differential equation. You integrate it, and what you get is, let's say, the point value of velocity. So the expression for velocity that you would obtain is going to be valid at all points in that flow field. There is a second approach which is slightly approximative in nature, that is called integral approach. You assume what would be the velocity profile in the region that you are considering. You have certain boundary conditions from the physical understanding of the system. For example, no slip or no shear, something like that. So with those boundary conditions, you should be able to evaluate what is the form of the assumed velocity profile. Then with certain equations and certain approximations, you should be able to find out what would be the average velocity through such a channel, what would be the average shear stress, what's the drag that the body is going to experience, and so on. Integral approach therefore is approximate, but if you can choose your boundary conditions properly, then it would still give you a very well engineering approximation of the whole flow phenomenon. So to begin with, we are going to study what is the differential approach in boundary layer, and then we'll move on to what would be the integral approach in boundary layers. These are all about hydrodynamic boundary layers. Now you can well imagine, and I have already discussed about the example of thermal boundary layer. Near a hot object, the temperature would be different than that of the bulk fluid. So this region where there is a difference in temperature is termed as thermal boundary layer. Similarly, concentration boundary layer or mass transfer boundary layer. If you let a block of salt in contact with flowing water, then the concentration of salt is going to be equal to the solubility of the salt at the interface. If you have a solid block of salt at the water salt interface, the concentration can be assumed to be that of the solubility of salt in water. As you move away, the concentration progressively decreases, and it would equal to the free stream concentration of salt over a very small distance. That is known as the concentration boundary layer. So any sort of change in velocity, temperature, or concentration is going to be confined within a very thin layer near the solid surface. That's the basic approach of boundary layer. There are many examples in real life where a concept of boundary layer is extremely important. For example, like you all have seen racing cars. Their shapes should be such that they are going to give minimum drag and maximum stability. Those are the two basic criteria for any design engineer to provide with a racing car. So how do you reduce the stress? How do you reduce the surface shear on such an object? How do you reduce the drag? One would be like if you can make the contour of of the racing car in such a way that you get minimum shear stress. Now, when you provide the minimum shear stress on the for the specific shape of the car, you also have to think about it should remain stable. Anything which when moves at a very high speed through any stagnant air, let's say, it's going to generate some sort of an wake at the back side of the car. So wakes are generally low pressure regions which would give some sort of an weightless feeling to the car. So its traction is going to be less. You'd like to break the wake so that there is no low pressure region formed at the back of the car. Because if you think of the car, the front end has a pressure. If the back end, due to the presence of the wakes, will have a low pressure region, then you have an opposing force. Okay, the car has to move against high pressure or against an unequal pressure. You'd like to break it. So they are using spoilers. You have seen spoilers. That's the projected end at the back of the racing car, which acts as wake breakers. Okay, you break the wakes, make them small so that there is no pressure differential between the front end and at the back end, which gives more stability and better gas mileage to the car. Examples are there from every field that you can think of. You all follow cricket, I am sure. Like when a fast bowler bowls a outswing ball and an in-swing ball, it all depends which way that stitches are pointed to. Because if you put the stitch in a direction towards the first or the second slip, which way the ball would swing, in or out? Outswing. So what's going to happen in that case is that those stitches will create turbulence on one side of the ball, not on the other side. So the result would be, turbulent and laminar flow, they behave differently. The stresses are going to be different. The drags are going to be different. So because of the unequal pressure on two sides of the ball, it would move in a specific direction. So while on air, when it's moving at sufficiently high velocity, due to this unequal pressure distribution on the two top ends of the ball, it's going to move in a specific direction. You can change the direction of the stitches and make the ball come in towards the batsman. That's an example of intelligent use of boundary layers. You also have seen that the bowlers purposefully keeps one side shining, the other side they make as dull as possible by repeated rubbing. The reason is the same. Keep one side shining so that there would be no localized turbulence, whereas on the other side, since it's rough, it would create local turbulence, unequal distribution of pressure. It would move in one specific direction. So that's another example of using boundary layers. Similarly, if you follow baseball, it's the same. There's a specific ball in baseball which is known as knuckleball, where it moves in the air in a direction that the batter cannot see until the point the ball is released from the hand. So if you are a batsman, you would definitely look very carefully about which way the seam is pointing, towards the first slip or towards you. Depending on that, it would move in a specific direction. So we are going to see all these things, how we can theoretically predict which way the pressure is going to be more, which way it's going to be the less. But let's start with a very simple basic diagram of an airfoil. You all know what an airfoil is. Okay? So it's roughly of this shape. And let's say I have flow of air towards the airfoil. Let's assume that this is stationary, the air is moving at a certain velocity. So at this point, what would be the velocity of air? At this point, the velocity of air would be 0. That's known as the stagnation point. And across this, the layer is going to generate and it would move in this. So any change in velocity is going to be confined within this thin region, which is called the boundary layer. So velocity would be 0 due to no slip here, and velocity would be equal to the free stream velocity, which I am calling as u infinity. So as if at an infinite distance from the airfoil, the velocity is equal to this approach velocity v. So velocity, approach velocity and free stream velocity, these two are different. If it's flow over a flat plate and I have approach velocity v, then that's at this point the velocity would be 0, and there would be an imaginary layer inside which the velocity would change from 0 here to u infinity at this edge. This u infinity is called the free stream velocity, and this v is known as the approach velocity. For flow over a flat plate, this v is equal to u infinity, only for flow over a flat plate. If it's not a flat plate, then v and u infinity may not be equal. We'll see why it is so. So we are going to concentrate on this region where the velocity varies from 0 to u infinity. Now let's think of what happens in a boundary layer. For a flat plate, with which we are going to be concerned most in our course, I am drawing the edge of the boundary layer. So this is the edge of the boundary layer. Velocity equal to 0 here. The velocity is equal to u infinity at any point and beyond. So over here, if this is u infinity, then the velocity would be slightly less, even less, and equal to 0. So if I draw the profile of velocity, it would probably look something like this. It would asymptotically approach that of u infinity. So the velocity profile starting from a value equal to 0, it would end up at u infinity in this fashion. Okay. So this is my velocity, and this is would be the distance. So velocity profile would look something like this. Now whenever we talk about this edge of the boundary layer, the question naturally comes, how do I define the edge of the boundary layer? Okay. It's easy to say that it's going to be the point at which the velocity, let's say that we call it u, the velocity is going to be equal to the free stream velocity, and that is the edge of the boundary layer. But looking at the nature of the curve, you can clearly see it's very difficult to pinpoint where this u equals u infinity is satisfied. Okay. It's an asymptotic nature. So one can read u equals u infinity at this point. Your friend can say no, it's at this point. And it's difficult to experimentally measure velocity over a very small region. Now you generally measure velocity, point velocity, using an instrument called Peter tube, which you are going to see in the fluid flow lab today. But how do I define it? The general definition for the thickness, boundary layer thickness, is where the velocity inside the boundary layer is equal to 99% of the free stream velocity. So velocity, where velocity is equal to 99% of free stream velocity, that thickness is termed as boundary layer thickness. It's another common name for boundary layer thickness is disturbance thickness. So you can see that any kind of disturbance due to viscosity is going to be confined within this region. Anything beyond this fluid doesn't know that a solid plate exists here. So, this is the traditional definition of boundary layer thickness for hydrodynamic one, and for thermal boundary layer and for mass transfer boundary layer it is again the same, 19, where the temperature approaches 99% of the free stream temperature. That is the thickness of the thermal boundary layer. It is defined in a slightly different way, but we will discuss about that. For hydrodynamics, this is the relation. Now, if you are an experimentalist, if you have knowledge about experiments, conducting experiments in a flow field, you will immediately object to this definition due to the error associated with the approach. Because as I said, who is to decide where the fluid liquid has reached 99%? You conduct an experiment, you get, let us say 3 millimeter be the value at which you can say velocity is 0.99 u infinity. Someone can do the experiment and say it is 3.5, and since the nature over here is asymptotic, you will definitely get some problems of these kind of inaccuracies. Apart from that, the measurement for velocity evaluation for 2 points very close to each other is extremely prone to error. So, there is definitely a need of defining alternate velocity or alternate thicknesses for boundary layers, which will not be point to point approach, rather they would be an integral approach. You all know from your numerical studies that if you differentiate a data, any error that you have in that data, it is going to be magnified. Whereas, if you can integrate over the data, then the small noises in the data are going to be suppressed. So, an integral approach is always preferred for data analysis than a point to point approach or a differential approach. The approach that I am describing here is finding the velocity at every point with experimental errors associated with it. So, how can we convert that to some sort of an integral approach? And this would give rise to two different definitions. One is the momentum thickness, and the second is displacement thickness. This is denoted by delta star and this is generally denoted by theta. Both of these are integral thicknesses. So, we would try to have in the first class, we would try to see what are these two, what are the advantages of using this approach over the boundary layer thickness. But one big advantage of boundary layer thickness or disturbance thickness is it's so easy to visualize, so easy to understand. So, that is why even though these are inherently inaccurate, the most of the literature refers to boundary layer in terms of boundary layer thicknesses and not displacement or momentum. But any sort of mathematical analysis, you have to depend on either displacement thickness or momentum thickness. So, let us see what these two are. A solid plate, liquid coming towards it, leading to the formation of a boundary layer. That is an imaginary layer inside which the viscosity effects are important, outside of which it is not. So, the velocity is slightly less here compared to the velocity outside. Now, how can we define some other thickness? So, let us analyze what is happening in here. The mass flow rate over this region is definitely going to be more than the mass flow rate in this region, since you have less velocity. So, can we define a way in which I can quantify the reduction in mass flow rate in this thin layer due to the presence of viscosity? So, the velocity here is u, the velocity over here is u infinity. So, we would like to find out what is the reduction in mass flow rate in this region. What is the mass flow rate? Rho times capital U times dy from 0 to infinity. Okay. This U is basically U infinity, that is the mass flow rate. If since U infinity is not a function of y, I can simply write it as 0 U infinity, I can simply integrate it. But because the velocity is no longer U infinity rather U, then this would be the reduction in mass flow rate inside the boundary layer, right. Previously it would be simply rho U infinity times whatever be the thickness over which the flow is taking place. It will be rho U infinity H, where H is the thickness of the layer which is flowing over the solid plate. But since I have a difference in velocity, this would be the reduction in mass flow rate due to the presence of the boundary layer. I am using 0 to infinity, but what should this be approximately? 0 to whatever be the thickness of the boundary layer. So, let us call it as delta, and I can see that delta is a function of x, where this is my x direction, this is my y direction. So, depending on where you are located on the actual position, delta will have different values. So, this infinity can very well be approximated by delta, which is the disturbance thickness, and this would give you the reduction in mass flow rate inside the boundary layer as a result of viscosity. Now, you would like to do it in a different way. Instead of keeping the solid plate over here, you have moved it up by some distance. So, this was the previous position and this is the new position. Okay. And let us assume that the flow here now is inviscid. That means there is no viscosity, but this much of area is unavailable to the liquid now, since you have moved it up by a distance, by some distance. Okay. Let us call that delta star. Now, what is the reduction in mass flow rate in an inviscid flow because you have moved it up by a distance delta star? Keep in mind that the velocity everywhere now is U infinity. So, the reduction in mass flow rate would simply be equal to rho U infinity delta star, because this much of area, let us talk about per unit depth, this much of area is unavailable for the fluid flow, and had this been available, the fluid would move with a velocity equal to U infinity, since it is inviscid flow. So, the total amount of reduction in mass flow rate would be simply rho U infinity delta star. By definition, delta star or displacement thickness is the reduction in mass flow rate in an inviscid flow when that is equal to the reduction in mass flow rate in the actual flow. Okay. So, this is the defining equation for delta star, which is known as displacement thickness. And obviously, delta star can be equated to 0 to delta This is the definition of displacement thickness. Maybe I should repeat it one more time. In viscous flow, due to change in velocity, this is the reduction in mass flow rate per unit depth. I would like to compare that for an inviscid flow by moving the boundary up by a distance delta star in such a way that the resulting decrease in mass flow rate, which is rho u delta star, is equal to the reduction in mass flow rate inside the boundary layer due to the presence of viscosity. When these two are equal, delta star is known as the displacement thickness. So, this is the defining equation for delta star. Now, let us talk about what would be momentum thickness. The reduction in momentum inside the boundary layer because of the presence of viscosity would simply be equals. So, this is the reduction in mass flow rate. If we compare with the previous expression, reduction in mass flow rate. What is the reduction in momentum? Multiply that with the local velocity, small u and capital U. I am just dropping the u in infinity sign. So, this is the mass flow rate, multiply that with the local velocity, integrate it over the y, that is the thickness of the liquid film which is moving past the solid object, and this would give you the reduction in momentum flow in a viscous flow over a flat plate. You can obtain a reduction in momentum by moving the boundary up by some other distance. So, you are not going to have any flow through this. Had there been flow in an inviscid one, the flow rate would be rho u infinity times some thickness, let us call it as theta, where theta is the amount by which you have moved the plate up. Now, this would be the reduction in mass flow, the same way we have done it before. Reduction in momentum, multiply it with another velocity. When these two are equal, this theta is called the momentum thickness. So, momentum reduction in momentum flow with the actual flow that is taking place inside a boundary layer. This the left hand side of the expression, when this is equal to the reduction in momentum in an inviscid flow due to the movement of the solid plate by certain distance theta, when these two are equal, this theta is termed as the momentum thickness. Okay. So, you can find out an expression for theta as well. It would be simply 0 to delta, no point in putting infinity here. It would be small u by capital U 1 minus small u by capital U times dy. This would be the defining equation for momentum thickness. So, are these two concepts clear to all of you? Any question that you would like to ask? Okay. So, one signifies the reduction, one definition comes from the reduction in the mass flow rate, the second one comes from the reduction in momentum of the actual flow that is taking place within the boundary layer due to the presence of viscosity, due to the slowing down of the fluid particles close to the surface. So, these two are the definitions of displacement thickness and momentum thickness. Advantages. What would be the advantages of using any of these two? If you can see, like this is the one, the small u that you experimentally evaluate, which will have errors associated with it. Okay. And u asymptotically approaches that of the free stream velocity. Okay. So, this is the region where you are going to have most of the problems. Now, here you see that those errors are going to be nullified or suppressed, since you are integrating it over a distance, not differentiating it or not using the value as such. You are using the integrated experimental measurements. Any noises are going to be suppressed. So, you can think of it as an infinite series. Okay. Initially, the contribution is going to be more. As you move in this direction closer to the edge of the boundary layer, all these terms are going to be smaller and smaller, and they would be exactly equal to 0 at the free stream, because at the free stream small u is equal to capital U. Okay. So, the contribution of this term would be smaller as I approach the free stream. So, even though I have errors in measurement of u, that error or the contribution of that error to overall theta or delta star would be minimal, because by definition those numbers are going to be very small. At this plate, on the plate itself, small u is 0 due to no slip. So, what you have is the maximum contribution to delta star near for a region close to this. Over here the contribution is less. Any error integrated, you do have a very accurate measurement of theta or delta star. So, that is the utility of expressing everything in terms of momentum thickness and displacement thickness. Any question? Okay. So, what we are going to see next is some fundamental relations associated with boundary layers. How can we express boundary layers in such a way that that would give us a way to mathematically treat the resulting equations. And the equation that we are going to use, it's a two-dimensional zero pressure gradient flow. So, I am going to write the Navier-Stokes equation for such a system and then simplify the terms and find out if we can have some sort of a governing equation with proper boundary conditions for boundary layer flow. So, I am writing the two-dimensional form of Navier-Stokes, zero pressure gradient, zero gravity flow. So, that means it is a case of a horizontal flat plate over which there is some flow resulting in the formation of a boundary layer. So, the expression would be for x component Okay. So, this part, as we have seen before, this is the convective momentum transport. This one is the diffusive transport of momentum. Navier-Stokes equation written for zero pressure gradient, flat plate and horizontal system. So, that means there is no effect of body forces. This one is the convection, convection, diffusion and diffusion. So, let us see if we can reduce this system, simplify this system for the present case. This del u del x and del v del y, can we say something about these two terms? Can we say something about the relative magnitudes of u and v? Remember, velocity in this direction is u and in this direction is v. So, since the principal flow is in the x direction, I can obviously say that u is going to be very large compared to v. It is laminar flow. So, since it is laminar two-dimensional flow inside the boundary layer, so u, the velocity in the x component, is going to be very large compared to the y component. Del u del x and del v del y, in fact this should be del u del y, it should be del u del y. Can we say something about these two terms? Del u, the variation of u with x and the variation of u y with y, obviously this variation is going to be much more compared to this variation. There would be some small variation of u with x, but the variation of u with y is definitely going to be much more. So, this would be the relation between del u del x and I can say that del u del x is going to be much smaller compared to del u del y. So, when we think of the product of these, I cannot cancel any of the terms, term 1 or 2. Let us call it as 3 and 4. So, 1 and 2 both remain in the governing equation. Is that clear? Now, let us think of del square u del x square and del square u del y square. These two terms signify that viscous transport of momentum or molecular transport of momentum in the x direction and in the y direction. Now, viscosity or viscous transport is going to depend on velocity gradient. more the velocity gradient, more would be the transport of momentum due to molecular motion with proportionality constant being viscosity. So, which one is going to be the higher one? Obviously, the term 4 is going to predominate over term 1. Since we know that the velocity varies small by a little amount in this direction, so the momentum transport, viscous momentum transport in this direction would be small compared to the viscous momentum transport in this direction, where the velocity changes from 0 to u infinity over a very small distance. So, this is going to be large, that means 4 is going to be very large compared to 3, as a result of which I should be able to cancel this term. Okay. So, my modified expression, governing equation for flow inside a boundary layer, hydrodynamic boundary layer, would be, this is momentum diffusivity del square u del y square. Okay. From an order of magnitude analysis and using the physical concepts which all of us now understand, this would be the governing equation for flow inside a hydrodynamic boundary layer. Convective transport, diffusive transport. So, how many boundary conditions do we need for solving this equation? 2 on y, 1 on x, right. So, that is basically the boundary conditions which we would need. Let us see what are the conditions that we can have for y. So, obviously, at y equal to 0 we can have some condition, and y equals infinity we can have another condition. So, what is the condition at y equal to 0? No slip condition. So, I am simply going to say u equals 0, and over here u is simply going to be equal to u infinity. So, that is the condition which we can choose for solving this equation. Any question up to this point? Another equation that one has to satisfy, this is Navier-Stokes equation. What is the other equation that the flow has to satisfy at all times? It is the equation of continuity, which is nothing but a statement of conservation of mass. So, that expression has to be satisfied in addition to Navier-Stokes for the flow at all times. So, I am going to write what is going to be the continuity equation and the Navier-Stokes equation. Let's denote them. I am denoting u as Vx and the y component as Vy. So, the first one is continuity and the second one is Navier-Stokes equation. These two equations will have to be solved simultaneously with proper boundary conditions to obtain what is the velocity profile, and if we have an expression for velocity profile, then we should be able to find out where the velocity reaches 99% of the free stream velocity, so that we can have an idea of where is the edge of the boundary layer. Now, we'll continue solving these two equations, but before that I'd like to ask you something. I am assuming that you already have an idea of what is a stream function. Okay, you all know what is a stream function, how velocity can be expressed in terms of stream function. So, if you define some stream function psi, then Vx is simply going to be equal to del psi del y, and Vy is minus of del psi del x, where psi is the stream function. And apart from other advantages which are associated with flow visualization using stream function, the mathematical advantage of stream function, can anyone tell me, like, what would be the mathematical advantage of using stream function in the light of these two equations? The stream function is defined in such a way that continuity equation is automatically satisfied. Okay. So, if you substitute in here, this is going to be del psi del x del y minus del psi del y del x. So, continuity equation is automatically satisfied by the use of stream function. And what is the mathematical property that the stream function should have, so that the order of it has to be an exact differential such that the order of the differentiation is unimportant. So, del psi del x del y is equal to del psi del y del x. For that, psi has to be an exact differential. So, the advantage apart from flow visualization and all which are associated with stream functions and streamlines, you have one less equation to deal with. So, I need to solve only this equation and not the continuity equation, which is automatically satisfied. So, I have to express this equation in terms of stream function. It still will remain as a PDE. It is a partial differential equation. So, my first thing would be how can I convert it to an ODE. Okay. And there are several methods. You probably have studied a few of them. One common one is similarity parameter. The similarity parameter approach is very simple. What we can see here, that my Vx, this is the dependent variable and the independent variables are y and x. It also contains some physical property, that is the kinematic viscosity. So, can we define a new variable, new independent variable which will contain both x and y, and it may contain some constants which are basically going to be physical properties. But the important thing is how do we combine x and y in such a way that when I use that similarity variable and substitute in this equation, it will change to an ordinary differential equation. There are several ways of doing it, and we are going to see in the next class how this thing is done for a very simple cases. I'll show you one method, and for most of the problems that you are going to encounter, that should be more than sufficient. How do we find out this similarity parameter? The approach that we are going to talk about is due to Blasius, someone called Blasius. So, it is Blasius 1 and it is a differential approach. Our governing equation is a differential equation. So, this is also called exact solution, which would be the topic of my next class. So, we are going to talk about the exact solution by Blasius, which what he did is he found the similarity parameter that works with this equation. With the proper boundary conditions, he was able to solve the equation for Vx, and once he has Vx, then he should be able to find out what would be the expression for delta. We are not going to go into the complete solution of Blasius. We will take a shortcut in between, that is, we are going to we are going to derive the what is the governing equation in ordinary differential form and then use numerical solution technique. So, I will give you what is the numerical solution for Vx from their delta. Now, if we can use our intuitive logic, we would be able to say that what this delta is going to depend on. Forget about mathematics, let us use our common sense. I have a plate and flow. This is the thickness of the boundary layer. If I increase the flow, are you going to have a thicker boundary layer or a thinner boundary layer? Okay, you are saying that its velocity it's going to be a thinner boundary layer. We will see about that. So, right now you are thinking that it should be a thinner boundary layer. If I increase the viscosity of the system, would the boundary layer thickness increase or decrease? D or I? I. Okay. So, delta should increase when you increase the viscosity. What about rho? Should I talk in terms of mu or mu by rho? Because if you think of mu by rho, what is mu by rho called? Kinematic viscosity. Any other term for kinematic viscosity? Let's work out what's the unit of mu by rho. All of you have done this problem many times. Mu by rho. Okay. What we are going to see is we'll see what's the unit of mu by rho. What's the unit of DAB, which is the diffusion coefficient? Meter per second, meter square per second, meter square per second. Sure. Okay. So you can figure out what is going to be the unit of mu by rho, and we are going to start our next class with, is there any relation between DAB and mu by rho? We know that DAB is called the mass diffusivity, and mu by rho is called the momentum diffusivity. Okay. You would see, you can do it yourself and see that it will also have the unit of meter square per second. So if this is momentum diffusivity, then we should not talk in terms of mu only. We should talk in terms of some sort of a diffusivity, because diffusivity is the one which controls what would be the thickness of this. As far as the momentum diffusion is concerned, if that diffusivity is more, the layer is going to be thicker. If momentum diffusivity is less, it is going to be like this. And in the extreme case where mu is 0, in viscid fluid, the momentum diffusivity would be equal to 0, and you do not have any boundary layer. So higher the value of this momentum diffusivity, higher would be the thickness of the boundary layer. So we can also say that then delta is going to depend, would be some function of mu by rho. It should be some function of the approach velocity, capital U, and so on. So this relation, once we have this relation, then we would try to connect it with some sort of a shear stress. Exactly like solid friction, we would like to find out what is the liquid friction factor, because as an engineer you would be interested in finding out how much friction you have to overcome for moving a solid object in a liquid. So this expression for CF, the friction factor, and expression for the disturbance thickness, these are the two which we are going to derive in the next class. Thank you.